Welcome to The Deep Dive. Today we're digging into something pretty central for anyone wrestling with huge data sets. Delta Lake. If you've ever found yourself in that situation where your data lake feels more like a data swamp, unreliable, slow, just messy,
Okay.
you get the problem.
Oh, yeah. You want that rock-solid reliability you got from, say, old-school databases, but you absolutely need the scale, the flexibility of a data lake for today's data.
Exactly. And Delta Lake, well, based on all the source material we've gone through, the guides, the tutorials, all of that, it really positions itself as the bridge between those two worlds. It's this open source storage layer designed to bring that reliability and, importantly, performance to your data lake.
That's the promise. So
Okay.
our mission here is to, dive deep into these sources, break down what Delta Lake actually is, how it manages to pull this off under the hood, and fundamentally why it matters so much.
Right. And the core idea, as the sources explain it, seems to revolve around extending those standard Parquet files we all use with transactional capabilities. And it does this using something they call the delta log.
That log.
Yeah.
That's really the heart of it all.
Okay, so maybe let's back up just a tiny bit. Talk about that evolution first. We started with the relational database world, right?
Right. Systems like Oracle, SQL Server, fantastic for structured data, totally ACD compliant, which gave you those reliability guarantees, and pretty easy to use with SQL. But they just weren't built for the sheer scale, the variety, the unstructured, semi-structured stuff that started flooding in.
Which naturally led to things like Hadoop, Spark,
Yeah.
the big data platforms.
Exactly. These platforms, and especially file formats like Parquet, which is columnar, great for analytics. They solve the scale problem. Suddenly you could store petabytes pretty cheaply. But you often lost the reliability piece. No built-in ACID meant, well, data lakes could get really messy, failed jobs, inconsistent data, just a lack of trust. The sources often call it the drowning in data problem, even though you have all this data.
Yeah, the data's there, but can you actually use it reliably? So Delta Lake steps in as this layer, trying to fix that trust issue and boost performance too.
That's the core idea. It sits right on top of your existing storage. Could be cloud storage, could be HDFS, and it manages the data files you have there.
And how does it do that? You mentioned two main components.
Yeah, the sources lay it out pretty clearly. First, you've got the data files themselves. These are just Parquet files, like you'd find in any modern data lake.
Yeah.
That keeps things compatible, scalable, and you get the performance wins from columnar storage.
Okay, standard Parquet. And the second part, the secret sauce.
That's the delta log. It's this specific subfolder, usually called delta log, living right alongside your data files. And this log, well, that's the brains of the operation for a delta table.
Okay, so what's actually in that delta log folder? What makes it tick?
Inside, you find a sequence of files. The critical ones are these JSON files. Every single time you successfully change the table, create it, insert data, update something, delete rows, change the schema, even add a constraint that action gets recorded as a commit in a new JSON file. And these files are numbered sequentially, like 00000.json, 0001.json, and so on.
Wait, so even just create table, making an empty table, that creates a JSON file?
Yep, that's commit is version 0. It records the initial state, the schema, and like in the examples, adding a constraint might create version 2. These JSON files are atomic records of change, building up this complete ordered history of everything that's happened to the table.
Interesting. I saw CRC files mentioned too. What role did they play?
Those are checksum files. Think of them as integrity checks for the JSON logs, basically making sure the log files themselves haven't been corrupted or messed with. They're important for robustness, but it's the JSONs that really tell the story.
Okay. And then there were checkpoint files.
Right. So imagine your table has been around a while, lots of operations. You could end up with thousands, maybe millions of these little JSON files. Reading all of them just to figure out the current state of the table would get really slow.
Makes sense.
So Delta Lake periodically does this housekeeping. It takes a whole bunch of those JSON commits and squashes their information down into a single, much larger Parquet file that's a checkpoint. These checkpoints act like snapshots, making it way faster to reconstruct the table state because you can just read the latest checkpoint and then only the JSON files created after that checkpoint.
Ah, okay. So the delta log, this mix of sequential JSON commits and these periodic Parquet checkpoints, that's the definitive record of the table.
Exactly. The sources hammer this point home. The log is the single source of truth. Everything about the table's current state, its history, its metadata, it's all derived from that log. And that's absolutely fundamental for delivering reliability.
Reliability, which brings us straight to ACID. Atomicity, consistency, isolation, durability. the gold standard for databases. How does this log actually enable ACID compliance in a data lake setting?
It's totally central. Let's break them down. Atomicity first.
Yeah, the all or nothing deal.
Right. So the sources explain that any operation, even if it involves writing multiple Parquet files or doing complex updates, is treated as one single atomic unit. It either completes fully, successfully, and gets recorded as a new JSON file in the Delta log, or if anything goes wrong halfway through, maybe a network glitch, maybe you try to insert data that violates a schema constraint, then no commit entry is written to the log for that failed transaction.
So even if Spark, say, managed to write some temporary Parquet files before the error hit.
Exactly. Those files might physically exist on your storage for a moment, but because there's no corresponding commit in the Delta log pointing to them as valid, they're essentially invisible. They don't become part of the table. The transaction effectively never happened from the table's perspective.
Okay, like that example where someone tried to insert a row with a negative ID, violating a constraint. The Parquet file might have been written, but no log entry means it's just orphaned data.
Precisely that scenario. The log guarantees atomicity. If it's not in the log, it didn't happen.
Got it. What about consistency, making sure the table stays in a valid state?
This ties in very strongly with schema enforcement, which Delta Lake does automatically on write. The table schema is defined in the metadata within the log. When you try to write new data, Delta Lake checks, does this new data match the table schema? Same number of columns, correct data types.
And if not, it fails, right? Like trying to shove text into an integer column?
Generally, yes, it will fail the transaction, ensuring consistency. Although there's a neat detail the sources mention, Delta Lake will actually try to perform safe typecasting if possible. So if you try to insert the string 123 into an integer column, it's smart enough to cast that to the integer 123 and let it succeed. But trying to insert the string hello, that would definitely fail.
Okay, so it's strict, but with a bit of practical intelligence. Makes sense. How about isolation? How does it handle, multiple people or jobs trying to write to the same table concurrently?
This is where it differs quite a bit from traditional databases. Delta Lake uses something called optimistic concurrency control. Instead of locking the table pessimistically, saying, nobody else touched this while I'm working, Delta Lake is, well, optimistic. It basically assumes concurrent operations probably won't interfere with each other.
So it lets them all proceed.
Pretty much. It lets different processes read the table state and prepare their changes based on that state. The check happens only at the very end, when a process tries to commit its changes by writing a new JSON file to the log.
The conflict resolution is at commit time.
Exactly. When attempting to commit, Delta Lake checks, has anyone else modified the files or data I based my changes on since I started? If there's no conflict, or if the changes are on totally different parts of the data, the commit succeeds. If there is a direct conflict, say, two processes trying to delete the exact same file simultaneously, one of the commits will fail, and that process will typically need to retry its operation based on the newer table state.
Okay, optimistic concurrency. That feels more suited to the scale of data lake workloads than heavy locking. And finally, durability.
Durability is straightforward here. Once a transaction successfully commits, meaning its JSON file is written to the log, and the associated data files are written to the underlying persistent storage, like S3, ADLS, GCS, those changes are considered permanent and will survive system crashes. The log entry confirms the transaction, and the data itself is safely stored.
Right. The combination of the immutable log and the durable storage provides that guarantee. Okay, foundation laid. Now, how do you actually work with these tables day to day? Creating them, getting data in?
Pretty standard SQL, mostly. You'd use create table.
Yeah.
Using Delta. One key thing the sources really emphasized is the location clause. Using location lets you create what's called an external table.
Right. Managed versus external, that distinction matters, doesn't it?
Hugely. A managed table means Delta Lake, or the Metastore, like Hive Metastore or Unity Catalog, manages both the table definition and the underlying data files. If you drop a managed table, everything gets deleted, metadata, and data gone.
Uh-oh.
Yeah. But with an external table, you specify the location, say s3.myBucketMyData. If you drop an external table, only the metadata definition is removed from the Metastore. The actual data files sitting in that S3 path, they remain untouched. This is crucial for not accidentally deleting your data, especially highlighted in that quiz example about dropping a schema with Cascade.
Definitely something to be careful about. Okay, so tables created. How do you load data?
Several ways. Insert into is the basic append operation, just adds new rows. Then there's insert overwrite, which effectively replaces the entire table content with the new data you provide.
And interestingly, the sources pointed out that insert overwrite doesn't necessarily delete the old physical files immediately.
That's a key point. It just updates the log to say, ignore those old files. These new files represent the current version. The old files hang around, which enables things like time travel, which we'll get to. Another really useful one is copy into.
What's special about copy into?
It's designed for idempotent batch loading, typically from files sitting in cloud storage. Idempotent means you can run the same copy into command multiple times, pointing at the same source directory, and it will only process and load files it hasn't successfully loaded before. It keeps track internally. Super useful for reliable incremental loading pipelines.
Okay, that sounds robust. And how do you inspect the table? See its history or properties?
The describe commands are your best friends here. Describe history is fantastic. It literally shows you that list of commits, the JSON files we talked about. You can see the version number, timestamp, what operation was performed, write, merge, create table, who did it, and even details about the operation.
That seems incredibly useful for auditing and debugging.
Absolutely. Then you have describe detail. This gives you info like the format, delta obviously, the location path, the total size of the table, the number of files currently active. And describe extended goes even further, showing table properties, partition columns, if any, and importantly, things like check constraints that you might have defined. You can actually see the constraint definitions listed there.
Being able to verify constraints easily with describe extended is nice. Okay, let's talk about changing existing data. Updates, deletes, merges. These are notoriously hard in traditional data lakes because Parquet files are immutable. You can't just change a row inside a Parquet file.
Right, that's a core challenge Delta Lake solves elegantly. Because it controls the table state via the log, it doesn't need to modify existing files when you issue an update or delete.
It writes new files.
Essentially, yes. For an update, it identifies the files containing the rows to be updated. It then writes new Parquet files containing the updated versions of those rows and potentially unchanged rows from the original files. For a delete, it writes new files that simply omit the deleted rows. Then, crucially, it updates the Delta log to mark the old files, or parts of them, as no longer valid for the current version and points to the new files.
So the log orchestrates this copy on write kind of behavior for modifications.
Precisely. Now, rewriting entire files just to delete or update a few rows can be inefficient, especially in large files. That led to a more recent optimization called deletion vectors.
Ah, tell me about those.
Instead of rewriting a whole multi-megabyte or gigabyte Parquet file just to mark one row as deleted, deletion vectors allow Delta Lake to attach metadata to an existing file, essentially saying, ignore row number X within this file. It avoids the rewrite, making small targeted deletes and updates much faster and cheaper.
That sounds like a significant performance improvement for certain workloads.
Okay, this whole mechanism, never modifying files, just writing new ones and tracking everything in the log, enables one of Delta Lake's most famous features. Time travel?
Yes. Time travel is definitely a headline feature because the Delta log keeps that history of every version. And because those older data files aren't immediately deleted, remember insert overwrite, you can actually query the table as it looked at any previous point in time.
So if someone runs a delete command by mistake and wipes out half the table,
you're not necessarily sunk. If the underlying data files for the previous version haven't been physically removed yet, you can query that older state. You use syntax like select from my quotable version as of version number or select from my quotable timestamp as of timestamp string.
wow. And the sources showed an example, right? Querying version 3 after a delete happened in version 4.
Exactly. You could instantly see the data as it was right before the delete. It's incredibly powerful for debugging, auditing, or recovering from oops moments.
Can you do more than just query? Can you roll back the entire table? You can. There's a restore table command. Restore table my table to version as a version number, or using a timestamp. This essentially commits a new version to the log that reverts the table's state back to how it was at that specified older version. The sources had that nice example of quickly restoring a table after a panicked user deleted data, potentially saving the day.
Okay, but there must be limits, right? You can't store infinite history forever.
Absolutely not. That would get incredibly expensive storage-wise. Delta Lake has retention settings. There are two key ones. Log retention duration, which controls how long the historical JSON log files themselves are kept. Default is usually 30 days. And deleted file retention duration, which controls how long the actual Parquet data files that are no longer needed by the current version of the table are kept before they become eligible for deletion. Default is often 7 days.
Eligible for deletion. Which brings us to the vacuum command.
Exactly. VCUM is the command that permanently cleans up and deletes those old data files. Specifically, it removes data files that are older than the deleted file retention duration and are no longer referenced by any log entry still kept within the log retention duration.
Okay, crucial point. VCUM deletes the data files, not the log files themselves.
Correct. Log retention and data file retention are separate. Running VCUM is irreversible in terms of data recovery for those specific files. Once they're vacuumed, they're gone.
And this directly impacts time travel.
Massively. If you vacuum files needed for, say, version 5 of your table, you can no longer time travel back to version 5. The sources had a really clear example. They vacuumed with a 0-hour retention, making time travel to a very recent version, version 8, fail immediately because its old files were gone. But time travel to a much older version, version 2, still worked, because the files needed for version 2 hadn't aged past the retention threshold yet when vacuum ran. So you need to configure retention and use VACUM carefully, balancing storage costs with your time travel needs.
Got it. VCUM is powerful but potentially dangerous for history. Okay, related to managing table states, what about cloning, copying tables?
Yes, Delta Lake offers cloning, which is a way to create a replica of an existing Delta table. It copies the metadata, the history, and potentially the data.
And there are two types, shallow and deep. What's the difference?
Big difference. A deep clone copies everything. It duplicates the entire Delta log history and makes brand new copies of all the underlying Parquet data files. It takes longer, uses more storage, but the result is a completely independent table. Changes to the original source table, including VSCUM, have absolutely no effect on the deep clone. The sources showed this independence clearly.
Okay, so deep clone is a full, isolated copy. What about shallow clone?
A shallow clone, sometimes called a light clone, is much faster and cheaper to create. It copies the Delta log metadata, and this is the critical part, it does not copy the data files. Instead, it simply points to or references the original data files belonging to the source table.
Ah, so if you vacuum the source table...
That you could break the shallow clone.
Exactly.
If the source table's data files that the shallow clone's log relies on get deleted by a VSUM on the source, any query against the shallow clone that needs those files will fail. It's fast, it's space efficient, but it maintains that dependency on the source data's physical existence.
That's a really important trade-off to understand. Okay, shifting gears slightly. How do you track changes at the row level? Say you have a downstream process that only needs to know what records were inserted, updated, or deleted recently.
That's precisely what the change data feed or CDF features for. You can enable it on a Delta table, and it starts tracking these row-level changes.
How does it store this info? Another directory.
Yep. When you enable it using an alter table, set TBL properties, delta.enable change data feed in true command, Delta Lake creates a separate subdirectory, usually change data, alongside the main data in Delta log.
And you query this feed somehow.
There's a special function, table changes. You typically call it like select from table changes, myenable, start version, end version, or using timestamps. It returns the rows that changed within that range, along with metadata indicating the type of change. Insert, delete, update, preimage, update, post image.
What kind of use cases does this enable?
Oh, lots. You can build much more efficient downstream pipelines that only process the delta, the actual changes, instead of reprocessing the whole table. It's perfect for feeding data warehouses, synchronizing systems, or building detailed audit trails. The sources even showed how you could use CDF as a source for a streaming query, allowing you to react to inserts, updates, and deletes from the delta table in near real time.
Okay, CDF sounds very powerful for integration. So we've covered reliability, history, change tracking. But what about raw speed, query performance, especially with massive tables?
Right. Well, Delta Lake's log naturally provides some performance benefits through data skipping using the stats stored in the log, like min-max values for columns in each file, to avoid reading files that couldn't possibly contain data matching your query's filters for really large tables. That's often not enough. You need more explicit optimization.
And a classic data lake performance killer is the small files problem, right?
The absolute classic. If you end up with thousands or even millions of tiny little Parquet files from lots of small writes or certain partitioning strategies, query engines just choke. They spend way too much time opening, reading metadata from, and closing all these files instead of processing data. The sources had a great example. A simple average calculation took way longer on a table with hundreds of small files compared to the exact same data compacted into one big file.
So how do you combat that?
The main tool is the optimize command. Running optimize a tuple tells Delta Lake to intelligently compact those small files into fewer, larger, more optimally sized Parquet files, usually aiming for around 1G, though it's configurable. The goal is to reduce the file metadata overhead and improve scan efficiency. The sources showed Optimize taking like 200 small files and replacing them with just one large one, resulting in a much faster query.
And sometimes this can be automated.
Yes, especially in platforms like Databricks. Features like auto-optimize, which compacts files during writes, and predictive optimization, which uses ML to figure out the best time and way to run optimize in vacuum, can handle a lot of this automatically in the background. You'd see operations marked with auto true in the describe history output.
Okay, so Optimize handles basic compaction, but the sources went deeper into more advanced techniques: partitioning, Z-ordering, Bloom filters, and this newer thing, liquid clustering. How do you choose between them?
Yeah, it's not always obvious. A key factor the sources pointed out is the cardinality of the columns you filter on most often. Cardinality just means the number of unique values. Is it low, like day versus night? Medium, like product categories? High, like timestamps or user IDs?
Mm.
Or extremely high, like unique event IDs or long text fields?
Okay, let's start with partitioning. That's familiar from regular data leaks.
Right. Partitioning physically divides your data into subdirectories based on the values in one or more columns, like having year 2023, month 01, year 2023, month through, etc. If you filter on your partition columns, for e.g., where year 2023 and month equals 01, the query engine can skip reading all the other folders entirely. It's generally best for columns with low to medium cardinality.
But it can also cause the small file problem.
Exactly. If you partition by a high cardinality column, you can end up with millions of tiny partitions, each with tiny files. Also, the sources noted that because Delta Lake already has good data skipping based on file statistics in the log, partitioning a single column might not give as much benefit as you'd expect compared to a non-Delta Lake. However, partitioning by multiple columns together can still be very effective, like in the example reducing file scans from 6 to 2. General advice is to use it for large tables, terabytes, where individual partitions themselves will still be reasonably large gigabytes.
Okay, partitioning, good for low-medium cardinality, use with caution. What about Z-ordering?
Z-ordering is different. It doesn't create subfolders. Instead, it's a technique you apply using optimize my Pobl Zorder by col1, col2. It physically reorganizes the data within the Parquet files, trying to co-locate data points that have similar values across multiple specified columns. It's particularly good for improving data skipping performance when you frequently filter on high cardinality columns, or combinations of columns, that might not be well covered by the default statistics Delta Lake gathers, which are typically most detailed for the first 32 columns.
So it helps the engine skip data inside the files more effectively for specific query patterns.
That's a good way to put it. It makes the existing min-max statistics more effective for those Z-ordered columns. It needs to be run periodically via Optimize.
Got it. Then Bloom filters.
Bloom filters are another indexing technique, but they target extremely high cardinality columns. Think unique IDs, maybe email addresses, or certain text fields. You create an index on column name using Bloom filter. This creates a small probabilistic data structure for each data file. When you query with a filter on that column, example, where transactioned XYZ, the engine checks the Bloom filter first. The filter can definitively say, this value is not in this file, allowing the engine to skip reading it entirely. It's probabilistic, so it might occasionally say a value might be in a file when it isn't, a false positive, but it never gives a false negative. Great for fast point lookups on columns where Z-ordering doesn't make sense.
Okay, so Bloom filters for those needle in a haystack lookups on unique IDs. That leaves liquid clustering, the new kid on the block.
Yeah, definitely positioned as the next evolution. The sources mention the be like water analogy, aiming for flexibility and adaptiveness. Under the hood, it uses different techniques, often involving space-filling curves like Hilbert curves, to figure out how to cluster the data physically.
And what are the main advantages it's aiming for?
Several key goals. One is incremental clustering, the idea that data can be clustered somewhat automatically as it's written, reducing the need for separate, heavy optimized jobs. Another is flexibility, making it easier to change which columns you cluster by without needing to rewrite the entire table, which is a major pain point with partitioning or Z-ordering. And generally, it aims to provide better clustering effectiveness across different types of data distributions compared to Z-ordering. You define it using cluster by, col1, col2, when creating or altering the table.
Does it completely replace Optimize then?
Not necessarily, at least based on the current state described in the sources. While it aims for incremental clustering, it might not happen on every single write, and sometimes manual optimize might still be needed to fully consolidate files or enforce the clustering layout optimally. It's definitely an area of active development and improvement.
Man, okay. We've really gone end to end here, starting from the basic problem, messy data lakes, through the core of Delta Lake, the log, the ACD guarantees it provides, then diving into everyday operations, the power of time travel, tracking changes with CDF, and finally navigating this whole landscape of optimization techniques from basic compaction to advanced clustering.
It really paints a picture of how Delta Lake adds these layers of reliability, manageability, and performance on top of what used to be just simple file storage. It fundamentally changes the game for data lakes, making them feel much more like robust, trustworthy databases, but retaining that scale and flexibility.
Yeah, pulling all this together from the source material really underscores how much capability is packed in there. For you listening, honestly, the best way to internalize this is probably to try it out. Get your hands dirty, create a Delta table, look at the Delta log run, describe history, try and optimize, maybe even experiment with time travel or CDF. Seeing it in action really makes it click.
Absolutely. And maybe a final thought to chew on as you explore this. We talked about how Delta Lake's log provides built-in data skipping using statistics. Then we discussed partitioning, Z-ordering, Bloom filters, liquid clustering as additional optimization layers. How much of the benefit from these advanced techniques is truly additive on top of what the log already gives you? And could there be scenarios where, say, overly aggressive partitioning actually hinders the effectiveness of the log statistics, or vice versa? Or thinking about automation, how do you balance relying on things like auto-optimize or incremental liquid clustering versus the need for deliberate manual tuning with optimize and vacuum? Where's the sweet spot?